Hello everyone. My name is Prachiti and today I along with my team member Suraj will be presenting on the analysis of Ford-Fulkerson and Edmund-Karp algorithms. To begin, let's consider a real-world example. Imagine you're the manager of a transportation network and you need to determine the maximum amount of goods that can be transported from one location to another. This is where the maximum flow problem comes in, which is essentially a mathematical problem of determining the maximum amount of flow that can pass through a network with limited capacity. The Ford-Fulkerson and Edmund-Karp are well-known algorithms for solving the maximum flow problem in flow networks. Ford-Fulkerson algorithm was first introduced by L.R. Ford and D.R. Fulkerson in 1956 and later improved upon by J. Edmonds and R.M. Karp in 1972, resulting in the widely known Edmund-Karp algorithm. Before diving into the theoretical aspect of these algorithms, let's first understand what flow networks are and how the maximum flow problem is approached. Flow networks are the kind of directed graphs that can be used to model material flow from one special junction, that is the source vertex, where the material is produced, to another special junction, that is sink, where the material is consumed through the network. There are other junctions, that is the vertices, that lie in the path from source to the sink, making the network a connected graph. In this way, each vertex, apart from the source, has at least one incoming edge. Each edge of this directed graph has a stated capacity, that is, the maximum rate for the material that flows through it. Vertices of such graphs, other than the source and sink, act as conduit junctions that allow the flow of the material without accumulating it. A flow network follows certain rules, such as if a flow network graph has edge u, v, then an edge v, u cannot exist. Also, we need to assign capacity which has a value greater than 0 to each of the edges. And one more thing that we need to keep in mind is that self loops are strictly prohibited for such kind of flow networks. Apart from this, there are two constraints that a flow in the network needs to satisfy. First is the capacity constraint, where the capacity of each of the edges in the graph has to be greater than 0, which implies that the flow should also be greater than equal to 0 and cannot exceed the capacity which is stated for the edges. Another constraint is the flow conservation constraint, which states that the total flow into a vertex must be equal to the total flow out of the vertex, except for the source and sink vertices. With such kind of flow networks, we can model the maximum flow problem through which we can calculate the maximum material flow that can be sent from a source vertex to a sink vertex in the network by complying with the constraints on the capacity of the edges and the conservation of flow at each intermediate node. Now, talking about the application, there are certain number of use cases for such maximum flow problems. One is in case of communication networks, where the algorithm can be used to find the maximum flow of data through a network while minimizing the delays and the congestion related issues. Another use case is in supply chain management, where the algorithm can be used to optimize the flow of goods from suppliers to customers. It can also be used to minimize the overall cost and the overall management, including the timely delivery of the goods. Other than this, there are different kinds of use cases in case of image segmentation, airline scheduling, and census tabulation. Now we'll dive deeper into the Ford-Fulkerson method and we'll also go through its implementation and the basic building blocks that account for its working. In the field of flow network graphs, the Ford-Fulkerson algorithm is a classic approach for solving the maximum flow problem. It works by iteratively finding augmenting paths in a residual graph and incrementing the flow along these paths until the maximum flow is reached. While the basic concept of the algorithm is simple, Its implementation and analysis can be complex, especially in cases where the flow and capacities of the graphs are large. This method depends on three key concepts. Therefore, we would first study all of them before diving into the implementation. A residual network is a roadmap for manipulating the flow, that is either increasing or decreasing it for particular edges of the flow network in order to increase the overall flow. The residual network is a modified version of the original flow network that reflects the remaining capacity of each edge, which can be used to determine change in flow for edges in the original graph. To determine what all edges would be part of the residual graph, the additional flow that the edges can admit has to be greater than zero. For the purpose of increasing the flow of an edge u, v in the forward direction, we can calculate residual capacity by subtracting the flow for an edge from its capacity. We can also implement a decrease in the flow for an edge in the residual network to indicate the backward reversal. For that, the residual capacity would be just the existing flow. In this way, such kind of reverse edges enable the algorithm to revert back the flow. Another key concept is the formulation of augmenting paths. Using the residual network, we can identify paths from the source to the sink that can be used to modify the flow for particular edges to maximize the overall flow of the network. These are called augmenting paths. To augment the flow along a path, we find the residual capacity, which is the minimum capacity of all the edges in the path, and add this value to the flow of each edge in the path. The process of augmenting the flow can be repeated until no more augmenting paths can be found, at which point the maximum flow has been reached. In this way, the Ford-Fulkerson algorithm is based on a key lemma which states that if there is an augmenting path in the residual network, then the current flow is not a maximum flow. Another key concept is related to maximum flow, minimum cuts approach. As we know, Ford-Fulkerson algorithm repeatedly augments the flow along augmenting paths until it has found a maximum flow. Therefore, a flow can be called maximum if and only if its associated residual network has no augmenting paths left. We can use the maximum flow minimum cut theorem, which states that the maximum flow in a network equals to the minimum capacity of all the cuts in the network. And this can be used to define the algorithm's termination condition and find the maximum flow by finding the least cut. A cut of a network is a partition of the vertices into two sets, S and T, such that the source vertex falls in the S set and the sink vertex falls in the T set. The capacity of a cut is basically the sum of the capacities of all the edges that cross the cut from S set to the T set. Therefore, for calculating the capacity of a cut, we count only the capacities of edges going from S to T and not the edges in the reverse direction. However, for the net flow, we do consider flow from S to T and the one in reverse direction as well. Therefore, we can determine the net flow from S to T across the cut C for S to T using this particular formula where we account for the reverse direction flow and as well the forward direction flow. Now we'll be going through the step-by-step procedure for implementing the Ford-Fulkerson algorithm. Before diving into an example, let us go through the algorithm first. So as you can see, initially the flow of the graph is initialized to 0, and then the algorithm tries to find augmenting path P in order to augment the flow by determining the residual capacity for that particular augmented path. The flow is then modified by either incrementing it when the residual edge exists in the original graph and decrementing it when the edge does not. This process of flow augmentation is carried out by iteratively finding augmenting paths using a depth first search strategy until no more augmenting paths. Now let us go through an example to solve the max flow problem with the help of Ford-Fulkerson algorithm. As you can see, initially we have made the flows for the graph as 0 as we haven't touched upon any of the path and haven't conducted any kind of augmentation. So let us now consider a path to augment starting from S to V1, V1 to V3, V3 to V2, V2 to V4, V4 to T. Now over here we can figure out that the minimum capacity with which this path can be augmented is 4. So let us do that, and after filling up the flow we get the resultant graph as this one. Now let us take another augmented path, let's say from S to V2, V2 to V1, V1 to V3, V3 to T. Over here, now while figuring out the minimum capacity that we could fill for this particular flow, we can see that 4 is a minimum capacity value. So let us do that. And from there, we get the new graph to be as this one with the modified flow. Let us take another augmented path, which has to be unique, so we cannot repeat any of the paths. Let's take a path from S to V1, V1 to V2, V2 to V3, V3 to T. Over here, let's try to find out the minimum capacity with which this flow can be augmented. We can make it out that 4 is again the capacity for the flow to be augmented. So let us fill it out. After doing that, we get the resultant graph to be having flow values of this kind. From here, we can see that there's still scope for augmenting paths. So let us do that. Now we pick up the path from S to V2, V2 to V4, V4 to V3, V3 to T. Now here we can make out that the minimum capacity for the edge of this particular augmented path to be filled is 7. So let us now do that, and the modified graph that we get is this one. Now we can see that there's still scope for augmenting path. So let us choose path from S to V1, V1 to V3, V3 to T. And we can make out that the scope for filling out the capacity here is again 4. So after filling out the flow for the augmented graph, we get the resultant graph to be of this value. Now over here we can make out that there is no more scope for filling out the augmentation of paths, because let's say if we consider the edges from V1 to V3, it's blocked. From V3 from V4 to V3, it's again blocked. From V4 to T, it's blocked. And even if we try to take a path from S to V2, this one, and V2 to V4, but then again we are blocked afterwards. And in between, we see that V1 to V2 and V3 to V2 are like reverse edges, so we do not have scope for augmentation. And with this, we can associate the max flow min cut theorem, which says that if we do not have any augmented paths left, then we have reached the maximum flow for the particular graph. So let us try to perform the minimum cuts that could happen. Over here, we would get the flow for the S set of this cut, as 11 plus 12, which is 23. And over here for the T set, we would get the flow as 19 plus 4, which is 23 again. So
We can say that the maximum flow that we can achieve with this particular graph is 23.
now we'll discuss the correctness, termination, and efficiency of the Ford-Fulkerson algorithm. While talking about the correctness, the Ford-Fulkerson algorithm maintains it by complying with the capacity and the flow constraints at each iteration until there exists no more augmenting paths. The capacity constraint is defined at each step with the amount of flow sent through an edge cannot be exceeding its capacity. For the flow conservation, the total inflow and outflow of each vertex must be equal except for the source and sink vertices. For the case of termination of this algorithm, we can say that the algorithm terminates according to the max flow min cut theorem, which proves that the maximum flow in the network is bounded by the minimum cut capacity. Since there exists a finite number of augmenting paths and positive capacities, each augmentation increases the flow in the network, eventually leading us with the maximum flow when all the augmented paths are explored. The time complexity for this algorithm is O of EF, where E is the number of edges in the graph and F is the flow value. This time complexity arises because the algorithm may need to iterate over all edges in the residual graph multiple times before reaching the maximum flow.
Thank you, Pradeep, for explaining the Ford-Fulkerson algorithm. Now let's dive into Edmonds-Karp algorithm. The Edmonds-Karp algorithm is a variant of Ford-Fulkerson algorithm that was proposed by Edmonds and Karp in 1972. The Ford-Fulkerson algorithm works by finding the augmenting paths in the residual network, but it can fail to find the maximum flow if it chooses the wrong augmenting paths. As shown in the example, if the algorithm always augments through the vertex u to v, it would take 2 million steps for the algorithm to finish in the worst case. The Edmonds-Karp algorithm addresses this issue by always choosing the shortest augmenting path in the residual network, which ensures that it always finds the maximum flow. The major change in the Edmonds-Karp algorithm is the use of breadth-first search to find the shortest augmenting path. This ensures that the algorithm always finds the shortest path from source to sink in terms of number of edges. Using a breadth-first search also means that the algorithm processes the vertices in the sequence of their proximity from the source, which leads to significant reduction in the number of iterations required to find the maximum flow. One reason why Edmonds-Karp algorithm performs better than Ford-Fulkerson algorithm is its worst-case time complexity. The Edmonds-Karp algorithm has a worst-case time complexity of V times E square, where V is the number of vertices in the graph, E is the number of edges. Whereas Ford-Fulkerson algorithm has a worst-case time complexity of E times F, where F is the flow of the graph, flow value. Now let's look at the working example of the Edmonds-Karp algorithm. Let's look at the same example as shown by Prasidi to understand how Edmonds-Karp algorithm runs faster than Ford-Fulkerson algorithm. So we have this example where we have the source as S and sink as T. We move forward with the first step where we initialize the whole residual graph with 0, and as you can see the resultant flow is 0 here, and we move forward with our first path where we try to find the shortest augmenting path using breadth first search. So the first path is S to V1, V3 and T, and the next part here is to find the minimum residual capacity, and which is 12. So since we augmented and when you look at the resultant flow, you can see that we have augmented 12 with the whole path, and the step here is to create update the residual graph with the the existing flows and try to find new augmenting path. So we move forward with the step again. As you can see here, the the new path, let's draw it as S to V2, V2 to V4, and V4 to T. Here, when we look at the minimum capacity is 4, and we move forward with the augmentation, and similarly, like the previous steps, we have augmented 4 again in the resultant flow, and once the 4 is augmented, we again repeat the same step where we update the residual graph, and while doing the residual graph, we see that then we have updated the flows, and we create the new we try to find a new augmentation path which is S to V2, V4, V3 to T. And we see that the minimum capacity again is 7, so we update the flow with 7, and while looking on this we can see that there's no more when we look at the resulting flow we can see that there's no more augmenting paths, and this algorithm terminates when there's no more augmenting paths left. So we can see that the resultant flow is flown starting from the source is 12 plus 11, which is 23, and same goes where 19 plus 4 is 23, which flows into the sink. And we can definitely notice that this result matches with maximum flow observed in Ford-Fulkerson, and we can definitely notice that it runs faster in terms of steps than Ford-Fulkerson. Now that we have seen the working example of Edmund-Karp algorithm, let's take a look at the source code implementation of the Edmund-Karp algorithm. The first section here is the general breadth first search implementation, where it's the is the is the basic implementation of the breadth first search, where we add each vertex into the queue, and depending on the queue, we just try to iterate and try to find the shortest path. The second one is where the main Edmund-Karp algorithm starts. We start with a while loop where we try to augment the flow where there is a path. If there is a shortest path, then we try to augment that, and we try to find minimal residual capacity in this particular code. Once we have found the minimal residual capacity, we update that with flow, and then at the end we do again we do a residual capacity update, and we do it until there's no more no more augmenting paths left. And even that is what the terminating condition for the Edmund-Karp algorithm is. So here's we have taken the same example which we demonstrated just now, and when we run this example we do get the same value as 23. And this is pretty much the whole source code of how Edmund-Karp algorithm is implemented. Now that we have seen the working example of Edmund-Karp algorithm and the source code implementation of this algorithm, let's dive into its correctness, termination, and time complexity. The Edmonds-Karp algorithm correctness is very similar to Ford-Fulkerson's method, which is based on capacity and flow constraints. However, the Edmonds-Karp correctness is also dependent on BFS algorithm or breadth first search algorithm, which always finds the shortest path from the source to sink based on a number of edges. The algorithm terminates correctly because the augmenting paths found by the breadth first search always increases the flow by at least 1 unit, which means that the maximum flow can be found in most E iterations, where E is the number of edges in the graph. Therefore, the Edmund-Karp algorithm is guaranteed to terminate after a finite number of iterations. This is because the algorithm uses breadth first search to find the shortest augmenting path in the residual network, which ensures that each augmenting path found has a length that is strictly greater than or equal to the previous path found. Since the length of the path is bounded by the number of vertices in the graph, the algorithm will terminate after a finite number of iterations. Let's talk about the time complexity. The Edmonds-Karp algorithm, as mentioned earlier, has a worst-case time complexity of order of b times e square, where b is the number of vertices in the graph, e is the number of edges. This is because the algorithm performs at most v iterations, and each iteration requires a BFS that takes at most order of e time. The worst case scenario is when all the augmenting paths found have length order of v, and there can be at most order of v augmenting paths found in each iteration. Grouping these all conditions together, we achieve the order worst case time complexity, which is order of v times e square. In this way, we have tried to analyze how the Edmonds-Karp algorithm is more optimized than Ford-Fulkerson method. Now we know that Edmonds-Karp algorithm is more efficient implementation of the Ford-Fulkerson algorithm that uses breadth first search to find augmenting paths. In terms of the use case, both algorithms have real-world applications in domains like transportation networks, communication systems, electrical grids, and more. Also, their ability to efficiently solve maximum flow problem has significant practical implications. Overall, we have found that understanding these algorithms and their applications can be useful for solving a variety of problems related to network flow. Thank you.